welcome to module 25. This module is very important in GDNT. We are going to talk about datum shift. Basically, we are talking about the datum with MMC modifier, such as here. So there's quite a long, description about datum shift. Basically, it's talking about if the datum is a feature of size, and once the datum is not at maximum material boundary. For example, here maximum material boundary is 4.0. This is the worst case. And once it's not worst, for example, it becomes 4.1 or 4.2, then this part is allowed to shift, to displace, to move on the datum B. So if you look at the whole sentence, it's talking about this. So next, we're going to give one example to explain how this datum BM we are going to affect this position tolerance. There's two components, part number 1 and part number 2. Part number 1 is a base plate, and there's a bolt M4, and here's M5. There's two bolts. This green part is perfect. The distance is perfect. This blue one is the component we need to make the join. But before we make the join, we need to understand the function. So the function is pretty simple. We are going to assemble the blue part into the green part. So M4 supposed to be inside this small hole. M5 supposed to be inside this big hole. And as long as both of the bolt is inside, then the function is okay. So here is the assembly. Okay, so let's make the join. As we mentioned, to make the join, we should follow the 3 steps. First, understand the function, and we know that. Second, specify the datum. So we have datum A is the bottom surface, and datum B is this blue hole, because we assemble this bolt first. And this one is the tolerance the feature, or the feature to be measured. And this position tolerance is going to use the datum A, B is here, and the last one is datum C. And datum B is this side surface. The next, we already know the size of the both holes. We need to calculate out the position tolerance. What's the value should we put it here? In order to calculate position tolerance, we should always assume that the both hole, they are at the worst case. The worst case is smallest hole for both. For the datum B, the smallest hole is 4.0. This is worst case. For tolerance the feature, the worst case is 5.4. This is worst case. And then it's easy to calculate out what's the position value. 5.4 minus the bolt. The bolt is 5. So we get 0.4, or plus minus 0.2 deviation, because there's a gap. Since it's plus minus 0.2 allowed, that's why we should put position tolerance here 0.4, right? So we put 0.4 here. Again, let's repeat. For all of the position value, we should always calculate based on the worst case that we have learned in the previous module. Next, what about the tolerance the feature? We make it bigger. From 5.4 we increase to 5.6. If the hole is bigger, then this hole is allowed to deviate a little bit further. In our case, it's plus minus 0.3, because we use 5.6 minus 5, we get plus minus 0.3 gap. You see, there's a gap here, right? So that's why you can see here is moved, and we can say it's deviated of the position from the nominal position, deviated plus minus 0.3. So that means the deviation is allowed a little bit more. So that's why we need add another, bonus symbol here. As we introduced in the previous module, we add MMC modifier here. We call this bonus. The bonus means once the whole size is become bigger than 5.4, we are going to get the bonus accordingly. In our case, 5.6 means bonus will be 5.6 minus 5.4. We get 0.2, right? The base position is 0.4. Totally will be 0.6. So this is the total position allowed. Right? Basic position, bonus. Okay, so we can say that way. The tolerance feature, they can get maximum plus minus 0.3 deviation based if the diameter is become the maximum 5.6. What about the position deviation is more than plus minus 0.4? For example, this hole is deviated to the right 0.4, and we know there's going to be interference between the hole and the bolt. Here there's a 0.1 interference, so there's a problem for assembly. So how to solve this problem? Then we're going to ask help from the datum B. Currently the diameter of this datum B is 4.0. It cannot provide any help. So in order to ask datum B to give help, we need to make this diameter a little bit bigger. So let's make it bigger, 4.2. And once the whole size is become bigger, then there's a kind of little bit of gap between the M4 and 4.2. If there's a gap, then we can think maybe we can move the part a little bit. For example, we move this part totally to the left side, right? And we can move what? 0.1, because 4.2 minus 4, we'll get plus minus 0.1. For the gap is 0.1, so we can move either left side or to the right side, plus minus 0.1. So let's move. And once we move to the left side, then the interference here will be disappear. There's no more interference if we move the total part. So the assembly is okay now. The function is okay. Since the datum B, we are going to give the help for the tolerance feature by moving the component. Then we should acknowledge the help for datum B here. So that's why we need add MMC modifier after datum B. So basically this datum B tells you we can move the total part if there's a gap between the datum B hole and the mating part. Okay, here. So that's why the BM, we call this datum shift. Again, the name is datum shift. It's not bonus. Datum shift means the datum hole is allowed to shift, to move, to adjust. And once it's adjusted, it's going to provide indirect help to the tolerance feature and make the function okay. Okay, so from here we can understand why the SME standard give the name as a datum shift instead of bonus. Basically the BM is not bonus, it's shift, it's displacement is adjustment. Okay. Next, so we are going to see here the summary. If the diameter of the datum B is become 4.0, this is the worst case, then datum shift is 0. And if the diameter is become bigger, 4.2, then datum shift will become 0.2. Okay, so it's pretty good, right? Looks like it's pretty straightforward to calculate this one. Okay, let's give you a quick question how to calculate the datum shift. For example, if the actual size for this hole is 4.1, what's the datum shift? If the actual size, the tolerance feature is 5.5, what's the bonus? Right? And then we need to calculate what's the total position allowed in this case. Okay, in this case. So you can pause the video here, you can calculate it by yourself, and then compare the answer in the next slide. Okay, so let's find out the answer then. Since the diameter is 4.1, that means it's bigger than 4.0. So the datum shift will be 0.1. So here will be 0.1 here. The tolerance feature diameter is 5.5. The worst case is 5.4. So the bonus will be 0.1 because 5.5 compared with 5.4. So here is the bonus. Okay. The 0.4 is the basic position tolerance. So we add them together, the total position will be allowed 0.6. That means this tolerance feature or this hole is allowed to deviate left, right, plus minus 0.3. Right? Plus or minus 0.3. Okay. If the actual distance is 30.35, that means it's out of tolerance because the spec is plus minus 0.3. Okay, so that's the way we calculate out if the actual part we get all of the actual measurement, how to find out the position is good or not. Again, as we mentioned, in this case, in this simple example, we can calculate out the BM. Looks like a bonus, but if I give you a little bit further complicated example, you will realize that BM actually is not bonus. Let's see here. This is one of the example here. As we mentioned here, example number 1, if datum B have a perpendicularity requirement, that means it's allowed to have perpendicularity variation 0.2 m. So what does it mean here? It means datum B is allowed to tilt reference to datum A. Right? And here we're going to find the value here. If the hole size is 4.2, the first one, the position will be allowed 0.2, no bonus. If the diameter is 4.3, then there's a 0.1 bonus. So the total perpendicularity will be 0.3, right? Because there's bonus here, you see? If the diameter is 4.4, then the total perpendicularity will be 0.4, right? So this is the explanation of this perpendicularity. So what does it mean here? It means if the actual size is 4.2, then the actual perpendicularity should be less than 0.2, right? Similarly here, if the actual size is 4.4, the actual perpendicularity should be less than 0.4. right? So this is talking about, okay. So let's look at one example here. One example. What about when we produce the actual size is 4.2, perpendicularity allowed 0.2, but the actual perpendicularity variation is perfect. I mean, there's no perpendicularity error. It's perfect vertical to datum A. So in that case, we put M4 bolt inside, and it's still gap here, right? There's still gap. So the gap will be, for single side, it will be 0.1. That means it's still allowed to shift plus minus 0.1. So I repeat that again. If the actual perpendicularity is 0, then it's pretty good. It's still allowed to shift, right? It's still allowed to shift. Okay, to shift plus minus 0.1. What about the actual perpendicularity? It's 0.2. Let's think about it. The perpendicularity is not perfect. It's 0.2. As we know, it's allowed 0.2. The actual is 0.2. Then the perpendicularity is still okay. However, if we push the M4 bolt inside, then there's no room to deviate, to shift, to displace, to adjust, right? Because the hole is tilted. So you cannot adjust this part anymore. That means datum shift is 0 because you cannot move the part. So from here, we understand that datum B, the datum shift, is not only decided by the actual size, but also decided by the actual perpendicularity. There's more error of this perpendicularity, and the datum shift will become less, right? So we can see there's quite a lot of different factors that could affect the datum shift. So that's the reason we should always say the BN cannot be regarded as a bonus in many situations. I just give you a simple example, right? Okay, let's give you another example here. If the hole size is become the biggest one, 4.4, the actual perpendicularity is 0. In that case, we have a maximum datum shift, right? We're going to use 4.4 compared with the M4 bolt. So there's a maximum displacement here. You can move the part. Next question. What about the actual perpendicularity? Is 0.4. It's still okay because it's allowed 0.4. The actual 0.4. So the hole is tilted. Right? It's tilted. And you can imagine 4.4 tilt 0.4. Then you push the M4 bolt inside. There's no room to move the part. So the datum shift will become 0. Again, as we said, datum shift will be decided by the actual perpendicularity of datum B. Okay, so this is one of the situations to explain which kind of factor will affect datum shift. Next, we're going to see another example. In another example, then the datum shift even cannot regard as a bonus at all. We have learned that if the datum B become bigger, we can move the component and give the help to the tolerance feature. If there's an interference here, we just move the component to the left, then the interference will be disappear, right? The function will be okay. But what about the tolerance feature? There's two holes, not one, there's two. It's here, and then both of them, they should mount it M5 and M5 both, and this should be used the same datum B. You see here, 2 times. That means this one and this one, they have the same position requirement, and all reference to datum A, B, C, right? So let's imagine, even the datum B reaches the biggest size, which is 4.2, is it possible to help the tolerance feature, which one of the hole deviated to the right and another deviated to the left, and both of them, they have interference 0.1 and 0.1, and both of them, they are the biggest size 5.6. So can we move this datum B to the left or to the right to remove the interference as we did before? So let's move it to see how can we make this M5 and M5 mounted at the same time, right? So let's move to the left first. We moved the total component to the left, and this one is okay now. There's no more interference, you see here, as we've seen before. However, you may notice here the interference become bigger. So because once you move the component, you're gonna move all of them together. So that's why there's more interference here. So we can see the adjustment of datum B won't help the both of the tolerance feature at the same time. You cannot help all of them. You can help one of them, but another one will become worse. So that's the reason we say we cannot regard as BM as bonus. You cannot use it as bonus and increase the position tolerance to him and increase tolerance to him to here. You cannot do that, right? And what about we move to the right? And once you move the whole component to the right, and here is okay, but here there's more interference, right? That's pretty much the same that as previous example here. Okay, so next question here is, how can we verify the datum shift, right? The best answer is make the gauge. Make the gauge. Okay, how to make gauge? First, the gauge supposed to have datum A, right? You're supposed to have datum A here. This is the bottom surface, and then you're gonna have a datum B, and datum B here, you're gonna make a gauge pin or location pin at the worst situation or at the worst boundary. From here, the worst boundary of this hole is 4.0. So you just make a pin 4.0 here, 4.0. This is locating pin for the gauge. You locate part first. Next, you're gonna make the checking pin. This one is the checking pin, and this one is the checking pin. We're gonna push the checking pin at basic dimension. At basic dimension. And once this checking pin can be pushed inside, that means the position is okay. If there's interference, you can move this part a little bit if the whole size is become bigger, right? So once you move it, as long as the checking pin can be pushed inside, that means the position tolerance is okay. Okay, the size of this checking pin is based on the MMVC or MMVB, maximum material virtual condition boundary. We have explained that in the previous module. What is MMVB, right? So the MMVB is, we use the smallest whole 5.4 minus 0.4, and we get 5. So we get 5. Get 5. Okay. Again, repeat again. When we use the gauge to check the position, we should always measure the actual size at first. If the actual size is out of tolerance, then you are not allowed to use this gauge. Okay. All right. So we have the gauge to check the position tolerance if there's a BM. Okay, the gauge pin, the location pin, is a cylinder. As long as the actual size is become bigger, then there's a datum shift. Okay, so we are going to use this gauge to simulate datum shift. Okay, and let me give one more example. If the tolerance feature is deviated to the right, both of them to the same direction to the right, and their interference at the left here, and there's interference at the left here. So in that case, we can move the component using datum B, right? We can move a little bit, we move to the left, and then there's no more interference. So this is a situation how the datum shift is going to help the tolerance feature. It depends how the tolerance feature deviated. Sometimes they can deviate it to different direction, right? Sometimes they can deviate to the same direction but with different value, right? So there's quite a lot of different scenario that they're going to affect your datum shift. Okay. All right. So here is the summary of this datum shift. First, the datum shift is decided by the actual size of datum feature, right? And second, is also decided by the actual geometrical tolerance value. For example, the perpendicularity value of a previous example. Okay. All right. Next, I should repeat again. Datum shift is not bonus. Okay, it's not bonus, and we're going to use the gauge to simulate the datum shift. That's the 2 point we should provide it. Okay. There's a more case study. As we learned in the previous example, the datum B is the whole, and here we're going to teach you what about the datum B is the surface, and datum B is the second datum. Okay, so here first datum is A, is a center hole, and datum B is a surface, and we can specify the datum B in 4 different ways. First, BM we have learned, but we should explain what does it mean BM if datum B is a surface. The surface is not feature of size, right? So what does it mean BM? Next, BL. What does it mean BL? Okay. Next, there's nothing here. And the last one is BSC. We call this basic dimension. Basically, it's basic dimension here. So we are going to explain that one by one. First, BM. BM means maximum material boundary. If datum B is a surface and there's a profile tolerance 0.4 reference to A. Again, A is a center hole. So we know that based on this TD, the maximum and the minimum boundary will be like this. Phi plus 0.2, we get maximum material boundary is here. If you minus 0.2, this dashed line is the LMB, least material boundary. Okay, and once we have MMB specified after BM, that means the part will rotate around datum A first, and the actual surface of this datum B will contact the gauge Basically, gauge is a small flat surface here at 5.2. This is the MMB boundary. So here is going to be have the highest contact point, right? And then you locate the part. So make it simple. First, based on this profile, we need to find the boundary of LMB and MMB. If it's specified BM, then we're going to make a gauge at MMB position to locate part. Same way, what about BL, LMB? LMB means we are going to locate part with the gauge surface here at LMB position, which is 4.8. So the part will rotate around datum A and has highest contact point to the gauge surface datum B, right? And let's talk about the another one. How about there's nothing here? If there's nothing specified here, that means this gauge surface datum B supposed to be adjustable, move up or move down within the range of LMB and MMB. So what's the point to move up and down? The point is we can move up and move down unless the actual surface has the maximum contact with datum B. So you can see here, if there's nothing here, that means the gauge contact surface is going to move unless they have the maximum contact. What I mean maximum contact? We can say that way. You're going to have a minimum 2 contact point, right? Minimum 2 contact point. And once you reach the maximum contact, then this component is located. Okay, so that's the scenario 3. What about the last one, BSC? As we said, BSC means basic. So basic means you're going to locate part at the basic dimension, which is 5. So this is the fixed distance. This is the gauge datum B. And you're going to rotate component around datum A and then reach the highest contact point. Okay, so you can compare that we are allowed to specify different boundary behind the datum B, and it all depends on the function of the part, right? It depends on the function of the part. So based on different function and different specifications, the gauge will be different. Okay, but there's one thing I should repeat. Datum B is a surface and it is the secondary datum, and you are allowed to apply the MMB or LMB here after. So what about the datum is the first, the primary one. If datum A is the primary datum, in that case you can never apply the MMB here, because basically there's no MMB boundary. There's only one surface here. Okay, so again, if a surface is a primary datum, then you shouldn't put the MMB requirement after datum. You see, the previous example, the datum B is a surface, but datum B is the secondary datum, not first. Okay, in that case we can find the maximum material boundary and the least material boundary, reference to the previous one, datum. Okay, all right. Again, this is a kind of summary for the datum shift. So far we have explained that for the feature of size, usually we can apply it to the size. In that case, we call this rule number 1, or in ISO GPS we call this envelope requirement. and we can apply mass material MMC to the tolerance feature. In that case, we call this bonus, right? And we can also apply the MMC modifier to the datum. In that case, we call this datum shift. Okay, so you can, everything here is talking about the boundary of the feature of size, except the datum. The datum, if datum is surface and is not the primary datum, in that case we have MMB, maximum material boundary. Okay, I think that's it for the datum shift. We are going to see you in the next module.